So students, this is Gravitation 7 video and today's topic is escape velocity. First, we will study the definition of escape velocity, and it says the minimum velocity for a body to escape from a gravitational center of attraction of a massive body, that is to achieve an infinite distance from it. We will understand that what is escape velocity. Suppose this is the earth's surface, this is the earth, this is the center of the earth, and an object of mass m is placed on the surface of the earth. Now, due to the gravitational attractional pull, we know that earth attracts every object towards its center. So, this object of mass m will be attracted by the earth towards its center, and this gravitational pull, suppose this gravitational pull is affected or is applicable on the objects which is placed within this dotted line, and beyond this dotted line, if we place any object, then that object will not feel the gravitational pull of this earth. We know from our practical knowledge that if we throw any object in the upward direction, then after some time it will again come back on the surface of the earth, because at a certain height, after throwing at a certain height, the kinetic energy of that object will be 0, and then again it will start to move in the downward direction, and after some time it will reach the surface of the earth. But what if we throw any object with such a velocity that it just never come back on the earth's surface? For that we have to send that object beyond this dotted line, so that suppose we will send the object, or we will throw the object at this distance which is beyond this dotted line, and as I said that beyond this dotted line, or if any object cross this dotted line, then the gravitational pull will not affect this object. That is what that this object will no more be attracted towards the center of the earth. So the velocity by which we can throw any object beyond this dotted line to escape the effect of this gravitational pull is known as the escape velocity. Now this is the earth, this is the center of the earth, that is O, and the radius of the earth is capital R, and the mass of earth is capital M. Now we have placed an object of mass m, small m, at a distance x from the center of the earth O. So the gravitational attracting force on this object due to earth is gmm by x square. G is the universal gravitational constant, m is the mass of the earth, this small m is the mass of this object, and x is the distance of the object from the center of the earth. This is the same diagram where the object is placed at a distance x from the center. Now what we will do, we will move this object by a very small distance dx in the upward direction, and the new position of this object is this. So if this position, the name of this position is P, then we will move this position in the upward direction by a distance dx, and the new position is P dash. Now we know that if we move this object from the position P to P dash, work will be done on the object, and we know that work done equals to force into displacement. Now what is the force? The force on the object is due to the earth gravitational pull, and that is equals to g mm by x square. So this is the force, and what is the displacement? The displacement is dx. So here the displacement is dx. So what will be the work done? The work done will be gmm by x square into dx. So this is the work done if we move this object from the position P to P dash. In the definition of the escape velocity, we saw that the object which will achieve this escape velocity will go to an infinite distance from the earth. So if we move the object from P to P dash, and this distance dx is very small, then the work done is g mm dx by x square. So now we have to calculate the work done when we will move the object from the earth's surface to infinity. Now as this work done is very small, then we can write this as dw equals to gmm by x square dx, because the displacement is very small, so the work done will be also very small, dw. If we move the object from the earth's surface to infinity, so the displacement will be very high, so the work done will also be very large. So now we will write it as w equals to integration of gmm by x square dx, and the limit will be capital R, that is radius of the earth, to infinity. If we solve this integration, we will get that this gmm, all three are constant terms, so we will keep this outside, and we get 1 by x infinity to r, and if we solve this, we will get gmm by r. This is equation 1. What happens when we throw any object like this? If this is an object and we throw this in the upward direction, then at a point it will reach the maximum height, and this is the position. Now when this object is at rest, the kinetic energy is 0 and the potential energy is maximum, and when it starts to move upward, the kinetic energy increases and potential energy decreases, and at the peak point the kinetic energy is again 0 and potential energy is maximum. This happens just for a moment, just before starting the downward motion. The kinetic energy is 0 and potential energy is maximum. Then again, when it starts to move in the downward direction, the kinetic energy increases and potential energy is decreasing. And at when the object is again at the rest position, or again when it comes back on the earth's surface, then again the kinetic energy is 0 and the potential energy is maximum. Now we are denoting the escape velocity as VE, and the initial kinetic energy of this object is half mve square, because we know that the formula of kinetic energy is half mv square. So here, as the velocity is ve, so the initial kinetic energy of the object is half mve square. Now this is the escape velocity ve, and this half mv square is the initial kinetic energy of the object, and that should be equals to the work done gmm by r. This is the work done to move the object from the surface of the earth to infinity. So from the concept of work and energy, we can say that when this kinetic energy half mv square will be equals to the work done g mm by r, that means that at this moment the object, or when this is true, then the object will be able to escape the gravitational attraction of the earth. So to achieve escape velocity, this half mv square must be equals to g mm by r. Now here we will cancel out mm, half v e square equals to g m by r, that is equals to v e square equals to 2 g m by r, and from here we can say that VE equals to root over 2 g m by r. So this VE equals to 2 root over 2 g m by r is the equation number 2. We know that the gravitational acceleration, that is small g, equals to g m by r square. So from here we can write that gm equals to g into r square, and this is equation 3. And we can see that v equals to root over 2 g m by r, this is equation 2. So we will put the value of equation 3 in equation 2, that is we will put the value of gm equals to gr square in here, and then we will get v equals to 2g r square by r, and from here we can write VE equals to 2g, cancelling this r and r, we get 2gr. So this is equation 4, and this is the expression of escape velocity, that is VE equals to root over 2gr. This is the expression of escape velocity. Now from the expression of escape velocity, we can conclude that this expression is independent, or the escape velocity is independent of the mass of the object, that is small m, and this equation is valid for any other planets, that is we can calculate the escape velocity of any other planets using this equation. And what we have to do, suppose we will calculate the escape velocity of Jupiter, then we will have to take the radius of Jupiter, and we will have to take the gravitational acceleration, the value of gravitational acceleration of Jupiter. Then we can easily calculate the escape velocity of Jupiter using this formula. Now we will calculate the Earth's escape velocity. To calculate the escape velocity of Earth, we have to consider the value of the gravitational acceleration g, that is 9.8 meter per second square, and the radius of the Earth is 6400 kilometer, and if we convert it in meter, then it will be 6.4 into 10 to the power 6 meter, and the formula is VE equals to, the formula of escape velocity is VE equals to root over 2gr. So we have to put these values here, and then we will get, putting the values, we get that VE equals to 2 into, from g 9.8, and from r it is 6.4 into 10 to the power 6 meter per second, and it will be 11200 meter per second. And again, if we convert it in kilometer, we will get it as 11.2 kilometer per second. Similarly, if we calculate the escape velocity of moon, putting the values of g and r of moon, then the value will be 2.4 kilometer per sec.